In this video, we're going to talk about 8.8 improper integrals. Our objectives will be to evaluate an improper integral that has an infinite limit of integration. And our second objective will be to evaluate an improper integral that has an infinite discontinuity, meaning that it approaches a vertical asymptote. So far in calculus, we've evaluated integrals of very specific functions over very specific intervals. Namely, our functions have been convergent on finite domains. We'll talk about what we mean by convergent later. We interpret the integral of a function f of x over some domain a to b as the area below the function to the x-axis over the interval from a to b. That area representation only applies if the function is above the x-axis. Otherwise, we get, quote, negative area, and that really doesn't make sense, right, if we're below the x-axis, but the sign tells us whether we're above or below. We add those together. They're vectors. They get rid of one another, the part that's above and the part that's below, add together using the sign rules of addition of integers, and we see what the result would be if we would fill up that hole with the dirt that's on top. What would be left over? Would we have more hole or would we have more dirt? Something like that. So we now generalize integrals into two new cases where a or b or both are infinite. Those would be the limits of integration on a definite integral, or if f of x itself can blow up to positive infinity or negative infinity inside the limits of integration from a to b. So let's go ahead. Such integrals as case 1 and case 2 are called improper integrals, and that's our topic for today. Let's look at case 1, and we'll look at a graph here of the graph of e to the x, and it looks like so. Goes through 0, 1 here, and we're interested in at 3 e to the third is over here, and we're interested in all this area here. And this will make more sense once we get to chapter 9. What I'm asking here, but does this stuff here that I'm adding up, does it go to infinity, or does it go to some, does it get closer and closer to some number that this adds up to be something? So let's go ahead and look at how we would handle this one later, but that's just a look at it, that we see something that is, for case 1, we have a limit, an infinite limit here that we're going to negative infinity over here on the left. So that's case 1. Example of what that would look like if we have 0 to 1 of 1 over the square root of x, then we have asymptotic behavior at x equals 0. Square root of x is going to do something like this. And we're not going to have a left-hand side to that because x is not allowed to be 0 or negative inside of that square root. And so we're looking between 0 and 1. So the square root of 1 is 1. We have a 0.11 here. And we're interested in this area that is here, but this function blows up and goes towards positive infinity that way. So that's our example of case 2. Right. So let's look more at these cases. For case 1, improper integrals with infinite limits of integration. So first case, suppose a is a real number and f of x is continuous for x greater than or equal to a. and we have this integral from a to infinity of f of x dx. What we're going to do is we're going to stick a dummy variable b in place of the infinity and choose limit as b goes to infinity of f of x dx, provided that the limit exists. And we're going to evaluate this function here in terms of b with our fundamental theorem of calculus, and then we're going to find that limit and see if that limit exists. If the limit exists, then the integral is going to converge. If the limit does not exist, then the integral is going to diverge. So converge and diverge are going to be kind of maybe some big words here that we're going to talk about: convergence and divergence of these integrals. And that'll be a concept that's really going to pick up with and carry over into chapter 9, which we're getting ready for. So this is really laying the foundation for chapter 9 here. Suppose b is a real number and f of x is continuous for all x less than or equal to b, then we can go integrate from negative infinity to b of f of x dx. And since that's on the lower limit, we're going to let that limit be a. Choose that dummy variable there. A goes to negative infinity. And a to b, f of x dx, and provided the limit exists, the integral will converge. And if the limit does not exist, then the integral is going to diverge. Now suppose the f of x is continuous for any real number, and then let k be a real number that's somewhere in the middle there. We might actually use the letter c because we've chosen a and b, and let c be somewhere in between. That's typically what we're going to do. So I might forget to use the letter k, I might use a c, that's okay. But we can only have one kind of infinity on each integral, so we have one dummy variable. So I'm going to split it up at the letter k here and say that we're going to have negative infinity to k plus k to infinity, and we're going to let the negative infinity piece be replaced with a, and the positive infinity piece be replaced with b, and we're going to add those two integrals. If either of the integrals here diverge, it's divergent, so both limits have to exist. We'll talk about some stuff later about what if, well, just both limits have to exist, and it has to be for it to be convergent. So let's just leave it at that. We do not want an infinity minus infinity situation to try and say that that's zero. That's not necessarily going to be true. I think we've already talked about with indeterminate forms and things like that, that infinity is an idea, not a number, and I can't just subtract infinity from infinity and get zero. That's an indeterminate form there. And if either part goes to infinity, we're just going to say that the integral is divergent. So now in case 2, where we have a bad point, a bad number in between because we're going to a vertical asymptote, if there is a c value that is between a and b, actually we're going to let one of the endpoints be the bad number here to start off with. So if f of x is continuous on the interval from closed on the a side but open on the b side, because I can approach b but not get to it, with an infinite discontinuity at b, then when I try to integrate from a to b, I really need to integrate approaching b from the left-hand side. So I'm going to make that clear by putting a dummy variable in there in place of that number and saying the limit as that dummy variable approaches that number from the left, and I have a one-sided limit there. And if that limit exists, then the integral converges. But if that limit does not exist, then the integral diverges. Now let's go the other way, where it's open on the left-hand side and closed on the right. Suppose f of x is continuous on the interval open at A and closed on B with an infinite discontinuity at A, then we're going to, let's just show you what these would look like. So this, for example, would look like this. Here's x equals b, and the function is approaching from the left, and we're interested in that area there. Here we have x equals a, and we're interested maybe in this area here. All right, so again, number 2, open on the left-hand side because we have this vertical asymptote, closed somewhere on the right-hand side here at x equals b. There's x equals a. It's going to be closed over here. And then we want to know if I replace this lower limit with a c and limit as c approaches a from the right of f of x dx, then we're going to black. Then if that limit exists, the integral converges. If that limit does not exist, the integral diverges. Now, usually what we have, not always, but more typically we have something where we're given an interval from a to b with lower and upper limits, but there's a bad value c somewhere in the middle. And we need to split the integral so that we approach c from the left and c from the right. So first we go from a to c, where c is our bad point, f of x dx, and then c to b, f of x dx. Again, c is our bad point that we have to pull out. So we're going to stick a dummy variable k1 in place of c here as our upper limit, and we're going to let k1 approach c from the left. And then we're going to stick in k2, a dummy variable there. Again, we're usually not going to call them k. We're going to call them a, b, c, whatever we're going to call them. But a, b, and c were all used here to define these limits. So as the lower limit, we're going to let that k2 approach that bad number from the right in this limit. And then if, again, we have to have both of these integrals here have to converge. The limits have to exist on both of them for the integral to converge. So definition, if an improper integral gives a finite value, the limit is not infinite, and the limit actually exists, we say that the interval converges. If the integral does not exist or is infinite, we say that the integral diverges. So infinite. There we go. All right, so case 1, number 1, we have a limit at infinity here. We do have a bad point here at 0, but 0 is not in the limit, so I'm not worried about that. So we have 1 over x squared looks kind of like this, but I'm only interested in this from 1 to infinity over here. So you get an idea what this looks like here. And so I'm going to say limit as b goes to infinity of integral of 1 to b of x to the negative second dx. And then we have x to the negative first over -1 from 1 to b. The limit as b goes to infinity. It's going to be -1 over x from 1 to b. Limit as b goes to infinity is a -1 over b plus 1 over 1 is 1. Limit as b goes to infinity. Limit as b goes to infinity there is going to be 0 plus 1 is 1. And so this is convergent. All right. Second example here. Now we're going to look at 1 over x, which looks like that, from 1 to infinity, like so. We'll say, man, that looks like that's the same kind of thing. Shouldn't it do the same thing? We're going to see. I'm pretty sure it's not, based off of something that I know from chapter 9. So this is going to be limit as b goes to infinity of 1 to b, 1 over x dx. What do you know that's different? Here I use the power rule. Here I'm going to have to use the ln rule, right? So this is limit as b goes to infinity of ln of the absolute value of x evaluated from 1 to b is limit as b goes to infinity of ln of the absolute value of x minus ln of the absolute value of 1, which is just ln of 1. The limit as b goes to infinity, this is b. So limit as b goes to infinity of ln of the absolute value of b is going to approach infinity, which means the limit does not exist because it increases without bound. And so therefore the integral diverges. I'm just going to say diverges here. So we're going to learn a rule in chapter 9 that has to do with what this power is down here in the bottom. It's also right here in chapter 8. I'm not sure that we're going to get to the theorem, but I'll tell you the theorem right now. It says that, let me just go ahead and tell you this, that if I'm integrating from 1 to infinity of 1 over x to the p dx, that this converges for all p greater than 1, and it diverges for all p less than or equal to 1. We're going to come back to this idea. This will be important. This will show up in chapter 9 as a p series. When we talk about series and convergence and divergence of series, that a p series is going to be based off of this type of integral and has the same rules for convergence and divergence. The proof of this is in your textbook if you're interested in the proof of that, but just know that, and this doesn't have to be a 1 down there, that can be anything where this is going to be defined that's finite, but we start with 1 usually there. So if we're going from 1 to infinity of 1 over x to the p dx, that converges for all p greater than 1, diverges for all p less than or equal to 1. All right, let's move on to the next example. And we talked about this one specifically already, what it would look like, that we drew the picture and said that negative infinity to 3 over here. So let's let limit as a goes to negative infinity, a to 3 of e to the x dx. The limit as a goes to infinity of e to the x, evaluated from a to 3, is going to be e to the 3 minus e to the a, where this is limit as a goes to negative infinity. So I have to look at e to the x over here as I go to negative infinity, and that's going to approach 0. So this is going to approach e to the third, and it converges. Let's look at a more advanced integral here. So we have a improper integral because we're going to infinity here. So limit as b goes to infinity of 1 to b of 1 minus x e to the negative x dx. And we're going to need integration by parts here because we have an algebraic piece and we have a exponential piece. So remember Liate going to help us choose that u is equal to 1 minus x and dv is e to the negative x dx. So du is going to be a negative dx and v is going to be a negative e to the negative x. So I need a negative and a negative here, the negative all the way out front. Let's not lose track of it. So it's going to be a negative limit as b goes to infinity of, now we want u times v, so that's going to be a negative e to the negative x times 1 minus x. All that is getting evaluated from 1 to b minus this negative is going to be a positive limit as b goes to infinity of the integral of 1 to b of v du. So a negative negative is going to be a positive here, like that. So we can pull this negative out here now, and they will undo one another. So that's going to be limit as b goes to infinity of e to the negative b times 1 minus b minus e to the negative first times 1 minus 1. All right, plus limit as b goes to infinity of negative e to the negative x from 1 to b. All right, we got some interesting stuff going on here. So limit as b goes to infinity of 1 minus b over e to the b minus 0 over e, that's 0, plus, so this is, bring this minus out, this is going to be minus limit as b goes to infinity of 1 over e to the x from 1 to b. It's going to be, now the if I do direct substitution here, which I really can't do, I can't substitute infinity. But if I think about this, this is an infinity over infinity situation, and I can use L'Hopital's rule, or I can just use my stuff that I learned there about which functions grow faster. I'm going to apply L'Hopital's rule. So L'Hopital's rule here limit as b goes to infinity, and I want the derivative here with respect to b of 1 minus b over the derivative with respect to b of e to the b. And then this is minus limit as b goes to infinity over here of 1 over e to the b minus 1 over e, like so. So this is going to be limit as b goes to infinity of, when I take this derivative here, that's -1. I take this derivative, this is e to the b. So this is minus this out here. This is going to be minus limit as b goes to infinity, 1 over e to the b, plus limit as b goes to infinity of 1 over e. I don't really need that part because there's no b's in this. So 1 over e to the b, that's going to go to 0. That's going to go to 0. And I have a plus 1 over e. I just need to make sure that I kept track of all my signs here. So, oh yeah, I don't worry about this yet. So that gets taken care of over here. So this is going to be all these switch sign here. And then it's going to be plus minus plus minus, my answer is -1 over e. So it is convergent. I started to try and do my u substitution up here, and you don't do that. You just let the integration by parts take care of that for you because it's built in with u du and v dv. So, all right, let's go ahead and look at this next example. Now we have two infinite limits here. So I'm going to have limit as a goes to -infinity. I'm going to just pick a 0 as a good in-between point since 0 is within the domain. So let's just split this into -infinity to 0, 1 over x, 1 plus x squared dx plus 0 to infinity of 1 over 1 plus x squared dx. This is limit as x approaches a to 0 of 1 over 1 plus x squared dx plus limit as x approaches b of 0 to b of 1 over 1 plus x squared dx. So this is going to be an arctangent here. So limit as x goes to a of arctangent of x evaluated from a to 0 plus limit as x goes to b of arctangent tangent of x evaluated from 0 to b. So this is arc limit as x goes to a of arc tan of 0 minus arc tan of a plus limit as b goes to as this is supposed to say a goes to negative infinity, a goes to negative infinity, a goes to negative infinity. This is b goes to infinity, b goes to infinity, b goes to infinity of arc tan of b minus arc tan of 0. So this is limit as a goes to negative infinity of 0 minus arc tan of a plus limit as b goes to infinity of arc tan of b minus 0. It's going to be limit as a goes to negative infinity of negative, let's put negative over here, arc tan of a plus limit as b goes to infinity, arc tan of b. So now let's think what arctangent looks like. Arctangent looks like so, with limits here and here between y equals pi over 2 and y equals negative pi over 2. So this is a negative. As I go to negative infinity, this is negative pi over 2 plus, as I go to the right, it's pi over 2. So this is pi over 2 plus pi over 2 is pi, and it converges. Now let's think of a trig function where it has an infinite limit here. So we want limit as b goes to infinity of 0 to b of cosine of x dx. We're going to say that that's equal to sine of x. As b goes to infinity, sine of x evaluated from 0 to b. Limit as b goes to infinity of sine of b minus sine of 0. And you say, well, the sine function does this, but as I go out to infinity, it's oscillating. And we say, I don't know what this does. The limit does not exist. Oscillating behavior. Therefore, the interval diverges. Let's look at this next one. And I think this was motivating example number 2. If you remember, I said we would come back to it. So we have a bad point here at 0. So we're going to take the limit as x approaches, or as a here approaches 0 from the right. We can only approach from the right here. We're going to call this a, and we're going to call this 1. I'm going to rewrite this as x to the negative 1/2 dx. And we're going to say that we get limit as x approaches 0 from the right of x to the 1/2 over 1/2, or multiply it by 2 there. It's going to go a to 1. This is 2, limit as a. I'm not used to putting these dummy variables in here. I think you can tell. A approaches 0 from the right of 1 to the 1/2 minus a to the 1/2. It's 2, limit as a goes to 0 from the right of 1 minus the square root of a. And square root function here, as I come from the right, that is 1 minus 0 is 2. And that's convergent. Now we need to think about tangent of x, what it looks like. And it has asymptotes of pi over 2 and negative pi over 2. So we can only get close to pi over 2 from the left here. So limit as b approaches pi over 2 from the left, 0 to b of tangent of x dx. So this is a not so simple one to remember, but remember tangents related to secant. So this is ln of the absolute value of secant x from 0 to b here. And so this is going to be limit as b approaches to pi over 2 from the left, ln of absolute value of secant of b minus ln of secant of 0. So this is secant as I get close to pi over 2 from the left. Let's see here. So negative pi over 2 to pi over 2 is going to go to infinity here. So this is infinity because ln of infinity is also infinity minus 0. That's infinity, and it diverges. All right. Now let's think about this one. X to the negative 2/3, and it looks like so. And we have negative 8 over here. Oops, negative 8 over here, and positive 8 over here. And we're interested in this here. So we're going to have to split this up at 0, negative 8 to 0. Is our bad point. So we need limit as b approaches 0 from the left of -8 to b of x to the -2/3 plus limit as a goes to 0 from the right of a to 8 of x to the -2/3 dx is going to be equal to limit as b goes to 0 from the left of add 1 to this is going to be x to the 1/3. And then you're going to have a divided by 1/3 is going to give you a 3 there. And this is going to go from -8 to b plus limit as a approaches 0 from the right. Same thing over here, 3x to the 1/3, a to 8. So this is limit as b approaches 0 from the left of 3b to the 1/3 minus 3 times -8 to the 1/3 plus limit as a goes to 0 from the right of 3 times 8 to the 1/3 minus 3 times a to the 1/3, like so. So cube root of 0 is going to be 0. And then this is going to be -3 times -2 plus, and then 3 times 2 minus, that's going to go to 0. 6 plus 6 is 12. So this is convergent. Sorry, I ran out of room before I ran out of problem. But now let's look at the next example here. We have a bad point at 0 that's between -1 and 2. So let's set that up. -1 to 0, 0 to 2, 1 over x cubed dx. So I'm going to have limit as b goes to 0 from the left of interval -1 to b, x to the -3rd dx, plus limit as a goes to 0 from the right, a to 2, x to the -3rd dx, like that. It's going to be limit as b goes to 0 from the left, x to the -2nd over -2, evaluated from -1 to b, plus limit as a goes to 0 from the right, x to the -2nd over -2, evaluated from a to 2. And we limit as b approaches 0 from the left of -1 over 2b squared plus 2 times -1 squared, like that. And then this is going to be plus limit as a goes to 0 from the right of a -2 times 2 squared over 1 minus a negative is going to be 2a squared, like that. Okay, and then as I look at this, that this is going to be 1/2 minus infinity. And already when I see that, I know this is going to diverge. Because this is going to negative infinity here. I'm just going to show you this side also diverges. This is going to be minus 1/8 plus infinity. So this is infinity minus infinity. It's divergent. We only needed one side of it to diverge for the whole thing to diverge, but it's doubly bad there. Both of the intervals diverge. So now let's evaluate this interval here. And let's let u be equal to ln of x and dv be equal to x to the negative third dx. So du is equal to 1 over x dx. V is equal to x to the negative second over negative 2. We're going to write this as 1 to b, limit as b goes to infinity of ln of x over x cubed dx, and we're going to integrate by parts. Limit as b goes to infinity of, and then the first part is going to be u times v, so negative ln x over 2x squared, evaluated from 1 to b, minus limit as b goes to infinity, 1 to b of v du. I'm just going to write it all out here. U times v ln x times x to the negative second over negative 2. I'm going to write it just like it is up there. So I'm going to pull the negative 1/2 out. Limit b goes to infinity of ln x over x squared from 1 to b. I'm going to pull the negative 1/2 out. Limit b goes to infinity, 1 to b, 1 over x to the third, or x to the negative third dx. And then we have negative 1/2, limit as b goes to infinity of ln of b over b squared minus ln of 1 over 1 squared plus 1/2 limit b goes to infinity of x to the negative second over negative 2 from 1 to b. So we're going to have a situation where we'll go into infinity over infinity here, and we can use L'Hopital's rule on that first one. Let me just leave that one alone for a second. And say that we have minus a 0 here, plus 1/2 limit as b goes to infinity. This is going to become a -1/4 when I pull that -1/2 out here. And this is 1 over x squared, 1 to b. This is -1/2 limit b goes to infinity of ln b over b squared minus 1/4 limit as b goes to infinity of 1 over b squared minus 1. All right, so -1/2 limit as b goes to infinity. Derivative of the top is 1 over b. Derivative of the bottom is 2b minus 1/4. That's by L'Hopital's rule. Okay. Then this is going to be 0 minus 1 here. This is going to be -1/2 limit as b goes to infinity, 1 over 2b squared minus 1/4 of -1. So this is going to be -1/2 times 0 plus 1/4 equals 1/4, and that converges. That's our last example here. We'll come back the next time and start our discussion of Chapter 9 with sequences. Before we get into series, we need to talk about sequences first, because when we talk about convergence of series, we have to look at the sequence of the partial sum. So we need to know what a sequence is before we can talk about series. That's why 9.1 starts with sequences. All right, come back and we'll talk about 9.1 next time. See you for the next video.